there's a problem in the book about two balls that hit each other. I want to say elastically. Yep, the collision is elastic. And then, of course, there's an example in the book, the one we're looking at here. I call it H. That is an inelastic collision. And it's called a ballistic pendulum, and the two look kind of similar, except one is elastic and the other one is inelastic. And as you notice, I'm not recording every single problem in there, so here I made a choice that I'm going to do the inelastic collision, mainly with the reason that you also encountered in the book, and so here I have a chance to show you where the equation actually comes from that you find on the lab sheet. So here we go. Ballistic pendulum says a ballistic pendulum can be used to measure the speed of projectiles such as a bullet. The ballistic pendulum shown in this figure consists of a block of wood of mass 2.50 kilograms suspended by a wire of negligible mass. A bullet mass M1 equals 0.0110 kilograms fired with speed v01 just after the bullet collides with the block with the bullet in it, has a speed vf, and then swings to a maximum height of 0.650 meters above the initial position. Find the speed of the bullet assuming that air resistance is negligible. Okay, let's see what is given. They gave us the mass of the the mass of the bullet. They gave us the mass of the block of wood. They don't give us the initial velocity, but that's what they want to know. This one here is given, the mass of the block before the collision, because it's at rest. And then after the collision, well, we don't have that, but we should be able to figure that out. Okay, let's see. So before the collision and after the collision, I'm going to make an A here because this goes with drawing A. So before and after, we have M1 times V01. Gosh, that's smeared again. M1 times V01 equals, after the collision, the two are stuck together, so it's M1 plus M2 times their final velocity, so which means that actually after the collision these two are equal. I'm not going to put a question mark here because we don't have to calculate that. However, when we have this equation, then we have two unknowns. We don't know what this is. We don't know what that is. It's an inelastic collision, and because of that, during the collision itself, kinetic energy is not conserved. That means some kinetic energy is lost, so to say, and that's well due to the impact. You can imagine it has to get in there. It needs to need some energy in order to get in there and get stuck in there. Eventually, that's dissipated as heat, but we cannot calculate that. So during the collision, we cannot use the conservation of kinetic energy. But afterwards, we can use it. So part B, maybe I'll write this over here. Part B. Well, what we have here in part B is that it swings up, and that means the kinetic energy it has after the collision, which we don't know that, but the kinetic energy that it does have after collision then becomes a potential energy after the collision. Again, we don't know that, but let's see. We don't know either one of them, but let's see if that helps us. So I'm going to write here that yes, there's this called kinetic energy, and this one here is potential energy. Actually, I take that back. We do know the potential energy because we know what the height is and we know what the mass is of the two. Okay, so kinetic energy before it swings up, 1/2 times the combined mass times the velocity squared, and from the previous part we can just call this VF squared. We're not going to use velocity again, so we don't have to change any index here. And then that equals the combined mass, and I'm kind of running out of space, so I'm going to pull this over. There we go. So m1 plus m2 times gravity times the height. Okay, now I need more space. Okay, here of course we divide, masses divide in this energy equation, and actually I need to point out that the only unknown that we have here is VF, which means we could actually calculate what VF is. I don't do this. I don't do it though because I want to show you where the big equation came from on the lab sheet. So solving this one here for VF is going to be the square root of 2gh. And now I take that VF and I'm going to plug it in right here. So I substitute in there, and so I have m1 times v01 equals all the stuff that's on the right hand side, m1 plus m2, and you heard me say a moment ago that I said over here m1 times v01, but I didn't write that down because I divide by it. So divide this by m1, and then here's my substitution for the VF, the square root of 2gh. There we go. And that's what you find on the lab record, except yours is still a little bit more complicated. Notice that in this case here the wooden block rises up 0.65 meters. That's 2 feet that it goes up. When you do your experiment, your pendulum goes up such a small distance that you cannot measure it directly, and that's why on the lab sheet I use the trigonometric relationship between the angle that it extends, and you need the pendulum length, and you need to see how far it goes out, and that way you can calculate the h in here, and that's why the equation on the lab sheet actually looks more complicated than what we have here. This is if you're able to measure the height directly. And then when you plug in the numbers, you would come up with the result that they have in the book of 896 meters per second is what they calculated. About 3,000 feet per second for this bullet.